As these massive jets soared through the sky, their fate was already sealed. There were no distress signals, no desperate cries, only cold, calculated destruction as scientists watched as these airplanes came crashing with cameras rolling, capturing the violent collision. How far is too far when testing the limits of destruction? At what point does science cross the line into madness? Join us on this special episode as we reveal the 10 most brutal plane crash tests ever. Number 10. NASA's Big Experiment in the Desert. In the 1980s, NASA and the FAA teamed up for a bold experiment, deliberately crashing a real plane to test anti-misting kerosene, AMK, a special type of fuel designed to reduce fire hazards. They also wanted to collect as much data as possible on how the aircraft's structure, seats, and emergency systems held up in a crash. For this experiment, they chose a Boeing 720 fly since 1960. After over 20,000 hours in the air and over 54,000 takeoffs and landings, the aircraft was retired and repurposed for one of the most advanced crash tests in history. Crashing a plane isn't as simple as flying it into the ground. The team at NASA Ames, Langley, Dryden Research Centers, and the FAA and General Electric spent years planning every detail. They had to ensure the plane could be controlled remotely, that the test conditions were just right, and that they gathered as much valuable data as possible. Before the final crash test, the Boeing 720 underwent 69 practice approaches over a specially prepared site at Edwards Air Force Base. These flights allowed engineers to refine the remote control system and gradually introduce AMK fuel to study its effects. General Electric installed special degraders that broke it down into usable fuel to keep the engines running on the modified fuel. Inside the plane, crash test dummies occupied passenger seats equipped with sensors to measure the forces an actual passenger would experience. High-speed cameras and dozens of instruments were placed around the site to capture every detail. On the morning of the test, NASA research pilot Fitzhugh Fulton controlled the aircraft remotely from the ground. The Boeing 720 climbed to 2,300 feet before beginning its final descent toward the crash site. Everything was set for a controlled impact. The plane was supposed to hit the ground wings level, right on the center line of the runway, with the fuel tanks rupturing in a way that would allow scientists to analyze the fire. But things didn't go as planned. As the aircraft approached the ground, it drifted slightly off course and developed a Dutch roll, a side-to-side rocking motion that made it harder to control. At just 150 feet above the ground, there was no time to correct its path. The left wing dipped lower than intended, and instead of landing smoothly, the plane struck the ground at full throttle. The force of the impact caused the number 3 engine, on the right side, to tear open, spilling fuel directly into the fuselage. Within moments, a massive fireball erupted around the aircraft. Flames spread rapidly, and thick black smoke filled the cabin. The fire raged for over an hour before it was finally extinguished. The results of the AMK fuel test were disappointing. The fuel was supposed to prevent or at least slow down the fire, but while it reduced the intensity of the initial flames, it didn't stop the inferno that followed. Despite this, the crash provided crucial data that led to major improvements in aviation safety. FAA experts estimated that about 25% of the passengers could have survived the crash if they had escaped the fire in time. However, the cabin filled with smoke in seconds, making it nearly impossible for anyone to escape. This showed the need for better fire protection measures. One major change that came from this test was the introduction of fire-resistant seat cushions. The FAA used the data from the crash to develop cushions that could withstand flames longer, giving passengers more time to evacuate. Today, these cushions are standard on all commercial aircraft. Another issue was emergency lighting. Some lights detached from the plane upon impact, which could make it harder for passengers to see their way out in a real crash. This led to a new rule requiring floor proximity lighting to be mechanically fastened rather than attached with adhesive. The crash also revealed flaws in black box flight recorders. The data collected wasn't detailed enough to give investigators a complete picture of what happened during the impact. As a result, new regulations were introduced to ensure flight data recorders track more critical movements, including pitch, roll, and acceleration. NASA also concluded that pilots needed better tools to land safely in harsh conditions. They recommended using heads-up displays, which allow pilots to see important flight data without looking away from the windshield. Additionally, they suggested microwave landing systems, though in later years, GPS-based navigation systems, like the Wide Area Augmentation System, became the preferred technology. While the fire was an unexpected failure, the experiment ultimately led to life-saving improvements in aviation safety. Today, modern aircraft are better equipped to protect passengers in the event of a crash, thanks in part to a Boeing 720 that was sacrificed in the name of science. Number 9. The perfect plane test for entertainment. In April 2012, a team of scientists, engineers, and TV producers carried out a daring experiment in Mexico, crashing a real Boeing 727 to study the impact of a plane crash. Due to strict regulations, the U.S. wouldn't allow the test, so the team secured approval from the Mexican government and chose a remote desert site for the crash. The aircraft was packed with cameras, crash test dummies, and sensors to analyze the forces at play. However, since the plane had to fly over populated areas first, a crew was required for part of the journey. Captain Jim Bob Slocum and 3 crew members took off from Mexicali International Airport, followed by a Cessna chase plane. As they neared the test site, the crew parachuted to safety, leaving the jet to be remotely piloted by former Navy pilot Chip Shanley. Minutes later, the empty aircraft plunged toward the desert floor. At 140 miles per hour, the Boeing 727 smashed into the ground. The front section was obliterated, the landing gear collapsed, and the fuselage shattered. Cameras captured every second, revealing brutal destruction. Scientists rushed in to analyze the wreckage, uncovering striking findings. The front of the plane was destroyed, leaving no chance of survival for passengers seated there. Those in the middle, near the wings, were more likely to survive but would have suffered severe injuries. Surprisingly, the safest seats were at the rear of the aircraft, where crash test dummies mainly remained intact, proving that passengers in the back had the best chance of walking away unharmed. The test also confirmed the brace position's effectiveness and risks. While it helped prevent head injuries, it increased pressure on passengers' legs, leading to a higher chance of broken bones. Additionally, the plane's interior collapsed inward, making evacuation even harder. The experiment was filmed for a globally broadcast documentary on Discovery Channel and other networks. While some found it fascinating, others criticized the timing, as it coincided with a real-life crash in Nepal. Number 8. 1984 Fokker F28 full-scale crash test. In 1984, a team of scientists and engineers gathered at a remote test site in the U.S. to witness something extraordinary: a full-scale airplane crash deliberately staged for science. The aircraft chosen for this high-stakes experiment was a Fokker F28 Fellowship, a short-range jetliner. This was no ordinary test. It was an ambitious attempt to understand how a commercial aircraft breaks apart in a crash, and more importantly, how to make flying safer for passengers. The idea behind the experiment was simple but daring. By crashing a real airplane in a controlled environment, researchers could gather valuable data that no computer simulation or small-scale model could provide. This was the first time such a test was conducted with the full weight of modern aviation science behind it. The goal was to study how the aircraft structure held up, how fire spread after impact, and how passengers could survive a real-life crash. The Fokker F28 was stripped of unnecessary weight, but loaded with cameras, crash test dummies, and scientific instruments. Every inch of the plane was wired with sensors designed to record the moment of impact in extreme detail. The team worked for months preparing for this moment, running calculations, testing remote controls, and ensuring everything went as planned. The aircraft was fueled with a special mixture to make it as realistic as possible, allowing the fire to spread control after the crash, helping scientists understand how flames move through a plane's cabin. The plane was placed on a long track system, a massive rail that would guide it to a precise impact point. Unlike previous crash tests using small models or sections of aircraft, this was a full-size jet moving at a speed comparable to an actual landing gone wrong. As the countdown began, tension filled the air. Engineers checked their instruments, ensuring all cameras and sensors were recording. The plane was then released, accelerating rapidly down the track toward its fate. The moment of impact was violent. As the aircraft slammed into the ground, its fuselage crumpled and its wings snapped. Cameras captured the wreckage in slow motion, showing how the front of the plane took the most severe damage. In a real crash, passengers in this section would have had no chance of survival. The middle section, near the wings, fared slightly better, but the force of the impact would still have caused life-threatening injuries. The most surprising discovery was that the aircraft's rear remained relatively intact. The dummies seated in this section showed that passengers in these seats had the highest chance of surviving. This experiment, dramatic and destructive as it was, had a lasting impact on aviation safety. What seemed like a controlled disaster turned out to be a breakthrough in understanding how to protect passengers in the worst-case scenario. Number 7. The crash that changed aviation. In the late 1940s, airplane crashes were a serious concern, not just because of the impact, but because fires often turned survivable crashes into deadly disasters. Airlines were expanding fast, and safety had to keep up. That's when a group of aviation experts, led by American Airlines executive William Littlewood, pushed for a bold new approach, figuring out how to prevent fires after a plane crash. The task fell to Lewis Laboratory, now NASA Glenn, where researchers were determined to crack the mystery of crash fires. They didn't just want theories, they needed actual proof. So, they did something radical. They started crashing actual planes, on purpose. By 1949, they had their hands on around 50 worn-out twin-engine cargo planes from the U.S. Air Force. These planes had just finished the intense Berlin airlift, and they were so battered that pilots flew them to the test site with the doors open, just in case they had to jump out mid-air. The Army let them use an old WWII arsenal in Ravenna, Ohio, where engineers built a 2,000-foot-long runway for full-scale crash tests. These weren't just random crashes. Everything was meticulously planned. Planes were remotely controlled and sent speeding down the runway. They would slam into barriers that ripped off their landing gear and damaged the propellers, but the engines had to stay attached. Next, they slid through poles designed to tear open the fuel tanks, mimicking a real-life crash scenario. The goal? To see how fuel spread and whether a fire could be prevented. Scientists loaded each plane with instruments that measured heat, fuel spread, and structural damage to capture every detail. A fireproof box stored the crucial data, while multiple high-speed cameras filmed the crashes from every angle. The planes were painted white, and the fuel was dyed red so the footage would be crystal clear. What they found was eye-opening. Many pilots believed turning off the ignition before impact would prevent fire. It didn't. Others thought using lower volatility fuel would be safer. It wasn't. Bit by bit, old aviation myths crumbled under hard science. By 1957, the focus shifted from piston-engine planes to turbojets, as jet travel was becoming the future. Scientists even developed an inerting system that could cut off fuel and cool down the exhaust to prevent fires. Some airlines, like United, loved the idea, even though it added extra weight to the planes. But aircraft manufacturers? Not so much. Pratt & Whitney worried that drilling additional holes in their engines for the system would make them unreliable. Without government pressure, the idea never took off. Even a dramatic crash test film, narrated by the legendary David Brinkley, wasn't enough to convince manufacturers to invest in it. Despite proving that the system could save lives, airlines were reluctant to add the extra cost and weight. Still, the research didn't go to waste. Over time, aviation safety improved. Newer planes quietly started incorporating fire prevention features, and post-crash fires became much rarer. Lewis Laboratory, now part of NASA, kept pushing forward. They moved beyond preventing fires, focusing on better seat designs, seatbelt safety, impact resistance, and lightning protection. And when NASA needed experts to protect astronauts from rough landings in the Mercury space program, the scientists who studied airplane crashes were ready to help. In the end, what started as a daring crash test experiment changed aviation. It also helped shape the future of space travel. Number 6. NASA testing ELTs. Emergency locator transmitters were supposed to be game changers for aviation safety. Designed to send distress signals after a crash, these small devices were meant to guide rescuers to downed aircraft. But ever since they became mandatory in the 1970s, they've been plagued with problems, failing when needed, sending false alarms, or simply getting destroyed on impact. NASA had had enough. Instead of relying on lab simulations and theories, they intentionally put ELTs through the ultimate test: crashing real airplanes. Engineers prepped for the first crash at NASA's Landing and Impact Research Facility. They secured a retired Cessna 172, rigged it with cameras, sensors, and multiple ELTs, and then hoisted it 80 feet into the air. The goal was to simulate a rough landing, the kind that happens when a pilot miscalculates their descent. The countdown began, then release. The plane plummeted, slamming into a concrete slab with a deafening crunch. The nose crumpled instantly, wings folded inward, and debris shot into the air. High-speed cameras captured the carnage in detail as the aircraft came to a violent, shuddering halt. NASA's team rushed in. Had the ELTs worked? The results were frustrating. Some triggered correctly, sending distress signals as intended. Others failed. Antennas snapped off, rendering them useless. One even activated before the crash, proving how unreliable they could be. It was clear, ELTs weren't built to withstand real-world disasters. For the second test, NASA raised the stakes. This time they wanted to simulate a crash in a remote area, the kind of accident that strands pilots in the middle of nowhere. A second Cessna was lifted even higher, 102 feet, taller than an 8-story building. The target? A hard-packed dirt field designed to mimic the unforgiving terrain of backcountry runways. The cables were released and the plane plummeted. Unlike the first drop, this one twisted mid-air before slamming into the ground. The force tore the tail clean off, dirt exploded into the sky, and the cockpit folded like an accordion. Once again, engineers scrambled to check the ELTs. The results? Slightly better, but still disappointing. Some devices activated correctly, but others failed due to antenna damage or poor placement. One major discovery stood out: mounting mattered. If an ELT weren't secured properly, the impact would rip it loose, making it useless. If the antenna were too exposed, it would shear off before transmitting a signal. By now, NASA had learned a lot. However, they kept the details secret for the third and final test. Would they drop the plane from an even greater height? Add fire? Introduce water? The only certainty was that they wanted to push ELTs beyond their limits. Though the results haven't been fully revealed, one thing is clear: NASA's crash tests are already shaking up aviation safety. Their research has proven that ELTs, while better than they once were, still have major flaws. The data will be shared with aviation regulators, and if all goes well, new, more reliable ELTs could become standard within the next decade. Until then, pilots face an unsettling truth. The device meant to save them in an emergency might not work when they need it most. Thanks to NASA's extreme crash tests, which may soon change. Number 5. China's ultimate test. For decades, hypersonic passenger travel seemed like a distant dream. However, a groundbreaking test in China just brought it closer to reality. A hypersonic jumbo jet rocket reached an astonishing 5,000 miles per hour, fast enough to circle the globe in just a few hours. Imagine boarding a flight in Beijing and stepping off in New York in 2. It may sound like science fiction, but this latest experiment proves that technology is no longer just theoretical. The test took place at the Jiuquan Satellite Launch Center in the Gobi Desert. Unlike traditional aircraft, which rely on jet engines, this vehicle used a scramjet, a cutting-edge propulsion system that harnesses extreme speed to compress air for combustion. Without moving parts, scramjets are built for the violent conditions of hypersonic travel. The flight began with a rocket launch, propelling the vehicle into the sky before releasing it. Once free, the scramjet engine ignited, sending the aircraft slicing through the atmosphere at 5 times the speed of sound. At this velocity, the surrounding air didn't just push back. It became a force strong enough to rip apart weaker designs. Shockwaves pounded the structure, and the friction generated temperatures hot enough to melt steel. The aircraft's exterior burned like an inferno, surviving only because of advanced, heat-resistant materials initially developed for space travel. Every second of flight tested the limits of engineering. The immense aerodynamic pressure could have caused catastrophic failure without meticulous structural design. Sensors monitored airflow, temperature, and stress points, feeding critical data to scientists who must refine future models. Then came re-entry, a phase as dangerous as launch. Unlike spacecraft returning from orbit, this aircraft was already moving at hypersonic speeds within the atmosphere, making deceleration a major challenge. A wrong angle could send it spinning out of control, while the extreme heat from air friction threatened to overwhelm its defenses. Plasma formed around the aircraft, blocking communications, a problem engineers must solve before hypersonic travel becomes viable. Yet, after a grueling descent, the test vehicle slowed and landed safely. Scientists immediately analyzed the data, eager to see how the scramjet performed under actual conditions. Chui Kai, the project leader, acknowledged the enormous challenges ahead, noting that many once dismissed hypersonic travel as impossible. The road to commercial hypersonic flights is still long. Engineers must improve fuel efficiency, lower costs, and develop materials that endure repeated extreme heat exposure. But this test proved one thing: hypersonic travel isn't just a distant dream anymore. It's a rapidly approaching future. Number 4. The $81 million mistake. The test flight was supposed to be routine, demonstrating the F-35's capabilities at Eielson Air Force Base in Alaska. The $81 million stealth fighter aircraft was one of the most advanced warplanes ever built, designed for speed, agility, and unmatched combat efficiency. Pilots trained endlessly to master its cutting-edge technology, and every flight was crucial to keeping the fleet in top shape. But on this particular day, something went wrong. As the jet took off, everything seemed normal. The pilot followed procedure, accelerating smoothly as the aircraft climbed into the sky. The F-35 had been designed to handle extreme conditions, and flying over Alaska's vast, icy terrain was another test of its resilience. The airframe responded flawlessly, its powerful engine roaring as it gained altitude. It was just another routine flight for a moment, but then, in an instant, that changed. Without warning, the aircraft lost control. It wasn't clear at first what went wrong, but the jet suddenly veered off its intended path. The pilot fought to regain control, his hands scurrying across the controls, but the situation spiraled out of control faster than he could react. The F-35 was no longer responding as it should. It tilted dangerously, its flight pattern becoming erratic. Within seconds, the aircraft plummeted toward the ground. At this point, the pilot had one choice: eject. Training took over as he pulled the ejection handle, triggering a split-second sequence that could mean the difference between life and death. Explosive charges fired, launching the canopy away before the seat rocketed out of the aircraft. He was thrown into the open sky, the G-forces slamming against his body. The parachute deployed, slowing his descent, while the $81 million fighter jet hurtled toward the earth below him. The impact was catastrophic. The F-35 crashed onto the base with an explosion, sending a massive fireball into the air. Thick black smoke billowed upward, visible from miles away. Emergency crews rushed to the scene, sirens wailing as firefighters and medics worked quickly to secure the area. Miraculously, the pilot survived. He landed safely after ejecting and was quickly taken for medical evaluation. The fact that he escaped unharmed was nothing short of incredible, but the real questions were just beginning. What had caused the crash? Was it a mechanical failure, a software glitch, or something else entirely? The investigation started immediately. with teams from the Air Force and Lockheed Martin examining every possible angle. The F-35 program was already one of history's most scrutinized military projects. It was a plane meant to be the future of aerial combat, but it had faced numerous setbacks, from cost overruns to technical challenges. Now, with one of the jets destroyed in a fiery crash, the pressure to find answers was even greater. Investigators combed through the wreckage, looking for clues. Black box data was retrieved, flight records analyzed, and maintenance logs reviewed. Every detail mattered. As the days passed, theories emerged. Some speculated it was a technical malfunction, a failure deep within the jet's complex systems. Others considered it a pilot error, though those who knew the pilot insisted he was highly skilled and experienced. The Air Force remained tight-lipped, only confirming that a full investigation was underway. But one fact remained: a multi-million fighter jet was gone, and the Air Force needed answers. Number 3. The Airlander 10 crash. Measuring an impressive 302 feet in length, the Airlander 10 surpasses even the Boeing 747 and Airbus A360, making it the world's largest aircraft. On August 24, 2016, the Airlander 10 embarked on its second test flight from Cardington Airfield in Bedfordshire, England. The flight commenced smoothly, showing the aircraft's stability and performance. However, complications arose as it approached landing after approximately 100 minutes in the air. The aircraft's mooring line, which had been hanging free after an initial failed landing attempt, inadvertently snagged on power cables near the airfield boundary. This entanglement caused the Airlander 10 to climb to an excessive height, leading to a high final approach and a subsequent nosedive upon landing. The crash resulted in significant damage to the aircraft's cockpit, though, fortunately, no injuries were reported among the crew or ground personnel. The incident prompted an investigation by the Air Accidents Investigation Branch, which identified the mooring line's entanglement with power cables as contributing to the accident. In response to the findings, hybrid air vehicles implemented several modifications to enhance the Airlander 10's safety and performance. These included the addition of 2 large inflatable airbags designed to protect the cockpit during landing. These airbags are stowed during flight and deployed upon landing to cushion the aircraft and prevent damage. Number 2. Mirage 2000 strategy. On February 1, 2019, 2 skilled pilots of the Indian Air Force, squadron leaders Samir Abrol and Siddhartha Negi, took off on what was supposed to be a routine test flight. Their aircraft, a Mirage 2000 fighter jet, had recently undergone upgrades at Hindustan Aeronautics Limited and needed to be evaluated before it could be cleared for active service. The modifications aimed to improve its radar, avionics, and weapon systems, but the flight ended in a devastating crash at HAL Airport in Bengaluru. Test flights are always risky, as pilots push aircraft to their limits to ensure everything works correctly. Samir Abrol and Siddhartha Negi, experienced test pilots from the Aircraft and Systems Testing Establishment, understood the dangers but did their duty. Shortly after taking off, their Mirage 2000 developed a serious malfunction. The exact cause was unclear, but it quickly became uncontrollable, forcing them to eject. Ejecting from a malfunctioning aircraft is meant to be a last resort, but it should provide pilots with a second chance at survival. In this case, however, something went wrong. Both ejection seats fired as expected, launching the pilots away from the stricken jet. But instead of slowing their descent, their parachutes failed to open fully. With no way to control their fall, they plunged toward the ground. At the same time, the Mirage 2000 had crashed and exploded into a massive fireball. The pilots, having ejected too late and from too low an altitude, fell straight into the burning wreckage. The impact, combined with the fire, gave them no chance of survival. Witnesses at the airfield saw the disaster unfold. Some heard a loud explosion before seeing black smoke rise into the sky. Rescue teams rushed to the crash site, but it was too late. The pilots, who had dedicated their lives to testing and perfecting military aircraft, were gone. An investigation was immediately launched to determine what had gone wrong. Since the Mirage 2000 had just undergone upgrades, experts examined whether a flaw in the modifications could have contributed to the failure. Another primary concern was the ejection system. Usually, pilots who eject have a high chance of survival, but in this case, their parachutes had not deployed correctly. This raised serious questions about the reliability of the aircraft's safety mechanisms. The tragedy sent shockwaves through the Indian Air Force and the aviation community. Fellow pilots mourned the loss of two highly skilled officers. Tributes poured in nationwide, with many recognizing their sacrifice and bravery. Samir Abrol's wife, Garima Abrol, later posted an emotional message questioning whether the lives of Indian pilots were truly valued. Her words sparked a national conversation about the safety of indigenous defense projects and the accountability of organizations responsible for aircraft upgrades. HAL faced intense scrutiny after the crash. Critics questioned whether its upgrade process was thorough enough and whether proper safety checks had been conducted before the test flight. The crash also reignited debates about India's reliance on older aircraft and the need for stricter testing protocols. Number 1. F-16 ejection fail. On the night of June 30, 2020, First Lieutenant David Schmitz set out on a crucial training mission, a test of skill and precision that would challenge even the most experienced pilots. This was his first nighttime air refueling exercise, combined with a simulated enemy defense suppression drill. It was meant to be a learning experience, but a chain of failures unfolded that led to a heartbreaking tragedy. Schmitz maneuvered his F-16CM to connect with the tanker, but he struggled to secure a stable link. Several attempts failed, forcing his commanders to call off the refueling exercise. With the mission cut short, he was instructed to return to Shaw Air Force Base. But what should have been a routine flight home turned into a disaster. Schmitz miscalculated his approach as he lined up for landing and struck a localizer antenna near the runway. The collision caused severe damage to the aircraft's left main landing gear. Now flying a crippled jet, he had little choice but to attempt an emergency landing. On the ground, the control team quickly decided to use a cable arresting system, designed to stop jets in emergencies, to help bring Schmitz's F-16 to a halt. However, the damaged landing gear created an unexpected problem. As the aircraft touched down, its tailhook missed the cable, and the left wing struck the ground. The plane skidded violently, making it impossible to control. Realizing he had no other option, Schmitz pulled the ejection handle. Ejecting from a fighter jet is supposed to be a last resort, a desperate move that still offers a chance at survival. The F-16 is equipped with the Advanced Concept Ejection Seat 2, a system designed to save pilots in extreme conditions. But when Schmitz activated the ejection, only one of the 7 explosive charges fired correctly. His seat shot upward, but without the necessary force to separate him from it. The parachute never deployed. He remained trapped in the seat as he plummeted back to the ground, unable to escape. The impact was fatal. Investigators later uncovered multiple failures that contributed to the accident. One major issue was Schmitz's lack of daytime air refueling training. Standard protocol required pilots to practice refueling during daylight before attempting it at night. But Schmitz had been sent on the mission without that crucial experience. The ejection seat failure was even more disturbing. A critical component, the digital recovery sequencer, exceeded its recommended service life by over a decade. Usually, this system would have ensured the proper timing and sequencing of the ejection. However, due to a missing plug and expired parts, it failed when Schmitz needed it most. Maintenance records showed that part shortages had prevented the necessary updates, leaving the seat dangerously unreliable. Additionally, the decision to use the cable arresting system was made without consulting Lockheed Martin, the manufacturer of the F-16. This oversight, along with the maintenance issues, highlighted serious gaps in safety procedures. In the aftermath of the accident, the Air Force thoroughly reviewed its protocols. Maintenance teams were ordered to prioritize updates to ejection seats, ensuring no outdated components were left in service. Training procedures were revised to prevent underprepared pilots from being placed in high-risk scenarios. At Shaw Air Force Base, Those who knew Schmitz mourned the loss of a talented and dedicated pilot. Lieutenant Gerald Smith, a fellow officer, described him as deeply committed to his country, family, and love of flying. Schmitz had dreamed of becoming an Air Force pilot since childhood, earning his pilot's license at just 16. His relentless determination helped him graduate at the top of his class, securing an Air Force position. His hard work and passion were undeniable, and his loss was deeply felt. Thanks for watching. See you in our next video.